Good afternoon. This is Caroline Hazard with the Jump Into STEM team, and welcome to the Round 2 Challenge, Stop the Squander, Identifying Building Malfunctions That Waste Energy, and our webinar series. This is webinar number 2. Today we're going to do a quick overview of the website if you haven't seen it already on a previous recording. I'll touch base on our other challenge that's running right now, connecting the right data at the right time, and then we'll leave a lot of time for Stephen Frank from NREL to give an overview of new methods for fault detection and diagnosis in buildings. So with that, let me get started here. What is Jump Into STEM? This is a student design competition opportunity and a great partnership between Oak Ridge National Lab and the Renewable Energy Lab, National Renewable Energy Lab, NREL, and ORAO to offer internships to students that get selected through this competition process. So during the fall, we have a challenge series. This is number 2 in the series. We've got one running right now, and the third one will be coming up. So through those challenges, we will down select some finalists, the best of the best through those idea submissions, and those folks will compete for the finalist event competition in the spring. We're still working on the date. It looks like it will be in April or March. And those folks will compete for up to 6 paid internships at Oak Ridge National Lab or the NREL National Lab. So to find out more, you should visit our website, jump.ideascale.com. To give a sense of what's our overall objective here, we're really trying to target students at universities and colleges and seeking to advance the involvement of women and minorities in the STEM fields. The challenges are open to all, but we are particularly interested in building diversity in the STEM fields. We're also seeking to engage colleges and university professors in working with us in promoting the student design challenges. This is an opportunity for you to use these challenges as part of your coursework or perhaps as a add-on extracurricular activity. So that's a great opportunity. We already have a couple of universities doing that, so we'd love to have more join the fold. And ultimately, we're looking to motivate the creative thinking and ideation among students to help advance building research and innovation, including the bright minds of our future here. Is really a key goal for the Department of Energy and the labs. So welcome, and we encourage your involvement. So let's go over to a quick navigation of the site, jump.ideascale.com. Again, I've done some recordings of this before, so what I'm going to suggest is that if you're new to the platform, just go straight to the How It Works button, and there's a recording there that tells you a lot about how the website works, where to go to get more information, and the like. So this is the landing page at jump.ideascale.com. So go there first. And then if you're interested in finding out more about the specific challenges that are being offered, you can click this button. This is a slightly older picture where we only had round 1 open. Right now we have round 1 and 2, so you'll see 2 buttons today, and in the near future there'll be a 3rd button for round 3. So once you click that button, you'll end up with a card that looks like this on the right side of your screen, where you can read more about the specific challenge. In this case, it's the round 1 challenge, connecting the right data at the right time. And so there's lots of information here, especially if you scroll down. This is a static image for me, so I can't do that. But if you scroll down, you'll find more data resources, links to other information that can help you think about your ideas. This is where all the recorded webinars are from previous webinars, as well as additional links. So lots of info for you. Once you've formed your team and are ready to, you've thought about your idea and you want to submit it, you can go ahead and click this button that's up in the upper right corner, submit a new idea, and it will take you to a form that looks like this, where you can submit your idea. Essentially, you'll select which challenge you're working on, put in a title, tell us a little bit about what your idea is, maybe a little bit about your team. This is a clickable button, and you can upload your PDFs or other data files that you want to include with your idea to help the judges understand what you're suggesting as a winning solution. And then when you're ready, you can hit the submit button, and the moderating team will review your idea and get it posted. So pretty straightforward. Here's the schedule of events. As you can see, we're kind of moving along here in the fall semester towards the end of October. The round 1 challenge has been open, and the webinar series are all recorded and posted. We're currently in the round 2 challenge and conducting webinar 2, and we have one more next week. The round 3 challenges will begin in early November, and there will be a similar associated webinar seminar series for you to view in association with that challenge. Each of these challenges have a judging period right afterwards, where we'll review all the submissions and select the finalists, and then we'll promote those finalists, and then they will move towards a mentoring stage and then the final event in the spring. We've also got a couple of hackathons and jumpathon events that are regional in nature that you can find out more information on when you go to jump.ideascale.com. If there are ever any updates to the site, to the schedule, you can always go to our schedule button and find that out. So what is the story with round 1 challenge topic? This is a really special challenge where we're trying to address the hurdles of looking at a lot of data and when is the right time to use that data. So we would love students' ideas on how do we effectively review data, baseline it to suggest ways to improve energy use, what are experimental models to test or monitor and influence behavior, how might you visualize the data? So these are all the kinds of questions that are asked in this challenge. So, think about that, and again, definitely encourage you to review the previous recordings from other webinars where there's lots of ideas to help you think about your idea to suggest on what's a way to help connect the right data at the right time. So with that speedy introduction, I'm going to turn it over to Steve. Steve joined NREL in May of 2013 and works in the Commercial Buildings Research Group. His areas of expertise are electrical power distribution systems, DC power systems, linear and nonlinear optimization, and energy informatics. Prior to joining NREL, he completed a PhD at the Colorado School of Mines. So we're really fortunate to have Steve with us today. Welcome, Steve. I'm going to give you control, and if you have any issues with that, just let me know, and we can figure out how to fix it. Steve, are you there?
Okay, thank you, Caroline.
Yep, here we go.
Okay, let me see. Yep, I'm going to share. Yeah, and if you suddenly see that the presentation has stopped functioning, let me know so that we can switch back to you.
Sure.
All right,
sure.
Thank you.
I see your slide.
Okay, good. I'm happy to have the opportunity today I'm on the wrong slide here, so let me back up all the way to the beginning of the presentation to give a brief introduction to fault detection and diagnosis as a concept and algorithms that are in use in buildings. The goal of this presentation is to give some context for the round 2 challenge on fault detection, and to provide kind of a starting point for ideas. So it turns out that fault detection and diagnosis is a really active area of research, not just for buildings, but across many other industries as well. But even though it's a very active area of research, it's also kind of an industry area where there's a lot of growth opportunity, and there's a lot of open problems, and there's a lot of challenges that remain to be solved, which is why there's a Jump into STEM challenge on this topic. And so what I want to do today is just walk through kind of what is FDD, provide an example that we could sort of like walk through some of the issues that face developers of fault detection diagnosis algorithms for buildings, talk about some of the challenges, and then suggest some places that you might be able to go to get additional information to help you craft your ideas, or to see if somebody else has tried what you want to try, and did it work, did it not work, that kind of thing. So I think that the audience for this webinar is probably going to be fairly diverse. So I'm going to start sort of at the beginning, which is, what is a fault? And so I'm starting with a bit of a wall of text here, but we're going to work through it piece by piece. So basically, when we're talking about building faults, we're talking about improper or undesired configuration, state, or behavior in a building system or piece of equipment that leads to adverse system performance. Okay, so let's unpack that a little bit. The first part I want to unpack is the improper or undesired. So basically, anytime that we're talking about a fault in a building, we're talking about something that is wrong with the building or with its systems or equipment. So you may have poor performance in the building that's not related to a fault. The building just wasn't designed very well, or maybe it's a building that has a lot of energy consumption because it has some really high energy use loads in it, or something like that. When we're talking about faults, we're particularly talking about things that are wrong. And we're talking about things that are wrong in relation to the configuration, state, or a behavior that you're observing in a building system or piece of equipment. And I want to kind of note that because fault detection and diagnosis can be kind of a broad category, but how I'm going to define it today, it has to do specifically with the building systems and equipment, so the things that are integral to the building. So we're talking about the building itself, not necessarily the stuff or the people that you put inside the building. And finally, if you have this improper or undesired configuration, state, or behavior, it's going to ultimately lead to adverse system performance. So your building is not operating the way that you want it to operate. Either it's wasting energy, or it's not meeting some level of service that you would like it to meet. So it could be that the lighting is too low or too bright. It could be that the temperature is off, that people are uncomfortable, or the humidity is too high. Or it could be just that it's wasting energy, and therefore your utility bills are too high. But kind of regardless, in some way, the system isn't operating in a way that's optimal. So that's the definition of a building fault. And then I want to give a few examples that you might encounter in your home. So just for example, if your air conditioner in your house is not working, well, that's a fault. Same for if somebody took your thermostat and punched the temperature up to 90 degrees in the summertime, you probably consider that a fault because you're not comfortable. Your house needs to be a cooler temperature for you to be comfortable. You might also think about a fault as something like an open window in the wintertime, where that cold air is coming in, it's causing your heating system to run more than it needs to keep your house warm, and therefore you're wasting energy. And so I've kind of outlined these three because they sort of show some different places that faults can occur. With the air conditioner, we're talking about a physical piece of equipment that's not functioning. With your thermostat, you're actually talking about a control system. And finally, with the open window, you're talking about the building itself, what we call the building envelope, which is really the shell of the building, doors, windows, walls, roof. So more broadly, we can think about, especially in the context of a commercial building, where do faults occur? What systems do they affect? And the ones that are mainly addressed in AFDD algorithms, fault detection diagnosis algorithms are the heating and cooling system, which is often combined with the ventilation system, providing fresh air to the occupants of the building, the lighting system, what I just called the envelope, which is basically the walls, windows, doors, roof, or in the control system of the building. And then also not shown in this picture because it's not a building with a refrigeration system, but if you have a supermarket or a warehouse or some other facility that has refrigeration systems to keep food products cold, those systems can also experience faults. And so you may apply fault detection and diagnosis to those types of systems. Okay, so now that we've talked through what faults are, let's talk about fault detection and diagnosis. So fault we just defined. Detection is basically answering the question, is there a fault in the building, someplace in the building with some piece of equipment or some system? It's as simple as that. It doesn't tell you anything about what's going wrong. It just says something is wrong with my building. There is a fault. The diagnosis piece is answering the question, okay, if there is a fault, then what fault is it? Can I narrow down what exactly is going wrong so that I can find it and fix it? So fault detection diagnosis is often abbreviated FDD. So you may hear me say FDD. You'll also see automated fault detection and diagnosis, or AFDD. And the automated just means that the fault detection and diagnosis process is being performed by a computer system or a piece of software rather than by a person who's doing it manually. So it automates the process of fault detection and diagnosis, and then can report the FDD results to an end user kind of in an automated way. Okay, so if you saw the last webinar, you probably saw this graphic on the various types of FDD. And I want to dig into this just a little bit, mainly to illustrate that there are lots and lots and lots of ways that you can go about doing fault detection and diagnosis. All of these apply to buildings. They also apply to other industries. But the point here is that there's a lot of active research. You can go find papers in most of these categories fairly easily, read up on them. So if something strikes your fancy, there are certainly resources that you can go access to think through in more detail. So I want to talk about the three kind of top-level categories here: the model-based category, the qualitative category, and the data-driven category. Now, these come from a reference that you see down here, references Tatapamula and Brambley from 2005. This is kind of a seminal paper on this topic. And I have included this reference along with a number of other references at the end of the presentation. You'll be able to, I believe, download the PDF of the presentation and have a good starting point for finding more information. Let's just talk through these categories just briefly. So the model-based category, the idea here is that you use a physical model of a system or a piece of equipment, and then you compare what that model is doing to what your actual building is doing. And when you make that comparison, you can see if there's any differences. And those differences may indicate that something's going wrong in the building itself. And so by looking at the differences between the model and the actual building, then you can come up with a fault detection or a diagnosis. Now, the second method here, which is labeled qualitative, I'm actually going to focus on the rule-based subcategory because that's by and large the bulk of the qualitative algorithms that are out there. In the case of the qualitative category, you sort of have a model still, but instead of having like a physics-based model where you're actually crunching numbers and performing computations, you have a set of logical rules that define what you expect normal operation to be. And so by looking at those rules, you can compare them to what you're actually observing and see if the building is working the way that is intended. So to take our example of a window that's open in the wintertime from a bit earlier in the presentation, if a window is open in the wintertime, then you want to consider that a fault. So you might have a rule that says if the temperature outside is below 55 degrees Fahrenheit, then all the windows should be closed. And so then checking for a fault is as simple as kind of seeing if you're violating that rule. Okay, the third method over here is data-driven. And so data-driven is just another type of modeling that instead of relying on kind of a physical model of the system or a set of rules that you've developed, you're actually looking at the system itself using the data that have been generated to compare to what has happened in the past to what's happening right now and in the future and see if they line up. And basically the idea here is that if in the past your building has been performing pretty well, and you can use the data to build up kind of either a statistical model or some kind of machine learning model to predict how the building should perform in the future for a similar set of weather conditions or occupancy patterns or what have you. And then you can compare what you're actually seeing to this past performance and compare it to your prediction and see if there's an issue. And so if there is an issue, if there's a discrepancy, then you can flag that as a potential problem and flag it as a fault. So you can use any of these methods. You can use hybrids of these methods. In fact, some of the work that we're doing here at NREL combines the model-based and data-driven approaches together to kind of complement each other. And then there are some other categories that I didn't even have room to put on this slide that are in the original paper there. But the point again is to be aware of these different approaches in case you want to use them, and to go to the paper to kind of find a source, a starting point for looking up kind of the major contributions in these different areas. And then along those lines, I just want to point out that in addition to research and development, AFTD for buildings is an extremely active area of commercial product offerings. And just to give an illustration, there's a website called smartenergyanalytics.org, and this is also in the references. And just on that website alone, there are 28 companies listed that have talked to the DOE team that's running that website and said, hey, we have fault detection diagnosis products. We'd like to be listed on your website as a potential source for people to find these products. And there are many other companies that aren't listed on there. So another thing that you want to do is go look around and see what's out there. And then if you find something that's similar to what you're thinking about, maybe you want to see that, has it worked well in the past? How's that company doing? What are they not doing that you think you could do better, etc. All right, so that provides kind of some background on the topics of what's a fault and the topics of what is fault detection diagnosis. And now what I want to spend the next few minutes working on is working through an example of a fault and the fault detection and diagnosis process. So the example we're going to look at is the example of what's called an airside economizer. And you may not be familiar with this term, so I'm going to explain kind of what this is real quick. But what an economizer is it's a subsystem within an air handling unit. An air handling unit is basically an air conditioner for a commercial building. They look a lot like this. So this would be a typical rooftop unit. And kind of regardless of what kind of air handling unit you have, they have some similar systems. What these units are doing is that they're conditioning air for one or more interior zones or spaces in a building. So they've all got some common elements. There's a supply duct, which is the air that's going to the space. There's a return duct, that's the air coming back from the space that needs to be conditioned. They typically have an outside air intake, and then they have a fan pulling the air through. And then they have this outside air damper that controls how much outside air is coming through versus how much return air is coming through. And finally, there's some heating and cooling coils to condition the air. Now, this part on the left here with the outside air damper and the control system attached to it, that's called an economizer. And the purpose of the economizer is to help save energy. Okay, so let's talk a little bit about Economizer Operation. Basically, what happens here in an air handler is that depending on the temperature outside the building compared to the temperature inside the building, the control system will adjust this damper to optimize the temperature of the air that's coming through the system. And so I just want to point out a few terms because we're going to see them coming up in the slides that are going to follow. We call this the return air. We would abbreviate it RA. This is the outside air. We would abbreviate it OA. This is the mixed air, or MA. This is the supply air, or SA. And this damper is controlling how much of the mixed air is return air and how much is outside air. So what happens if it's hot outside? Well, when it's hot outside, you're doing what's called mechanical cooling. You're cooling with your cooling coil. So what the Economizer control system does is it closes this outside air damper so that you just get the minimum amount of outside air that you need. And then most of the air is being recirculated from inside the building. So in this example, we have return air at 75 degrees and outside air at 85 degrees. Well, it's more advantageous to cool down the cooler return air. So we close the damper, bring the return air through, use our cooling coil to cool it down, and then supply that to the space. But what if it's actually cooler outside? Well, it's very common that a commercial building might need cooling when the temperature outside is actually still pretty mild or fairly cool, because commercial buildings have lots of internal loads. So what happens in this case is that the economizer opens that damper up to allow more outside air to come through, and it doesn't recirculate the return air. So in this case, because the outside air temperature is 50 degrees Fahrenheit already, that's quite cool. We don't need to run our cooling coil. We can actually just supply this outside air directly to the space, not recirculate the return air, and do what is called free cooling. So we're providing free cooling energy to the system by leveraging the temperature of the outside air. So that's what's supposed to happen. But what happens if you have a problem? So a very common fault in an economizer is that the damper gets stuck. The control system may break, or maybe the communications was interrupted, or as my colleague Grant Wheeler was telling me yesterday, perhaps a raccoon crawls in there and dies. That happens. So when this happens, the damper gets stuck, and you are getting some combination of the outside air and return air that may not be optimal. So if we think about this particular case, it's hot outside, but our damper is pretty wide open, so our mixed air is much warmer than it needs to be. Well, that means that we have extra cooling that we have to do to cool down that hot outside air, and so we can consider that a fault. It's wasting energy. Now, something to think about is, how would you detect this? As it turns out, if we go back and look at the supply air temperature from the perspective of the people inside the building, the air is still cool. There's nothing wrong. The system is working fine. But we know that because it's doing this extra cooling, it's wasting energy, and your utility bill is going to increase. So what are some ways that you might detect this fault? Well, let me suggest a few. And these are, two of these are sort of rule-based approaches, and one would be either a data-driven or a model-based approach. So the first one here is if you had access to the control system, you can say, well, okay, let me see. Do I have a command for where the damper is supposed to be? And do I have a sensor that's telling me the feedback on where the damper is supposed to be? Do those things match? If not, that's probably a fault. Or you could look at the temperatures. You could say, well, I know that when the system is cooling, that it's always optimal to basically have my mixed air temperature not be any hotter than my return air temperature. So I'm going to check the difference between my mixed air temperature and return air temperature, and if the mixed air temperature is substantially hotter than the return air, I'm going to say, okay, that's a fault. Well, what if I don't have those temperatures? Well, suppose that I could look at the cooling energy for my cooling coil. Well, if I had a model, either a physical model or a data-driven model built up based on past performance of the unit, where I knew for a particular set of conditions, such as an outside air temperature and the occupancy pattern and time of day, etc., how much cooling energy I should be using based on all that stuff. And then I compare it to how much cooling energy I actually am using. If the cooling energy is too large, then you could say, okay, well, that's going to flag this as a fault. But of course, we have to think about, well, what kinds of sensors or measurements are required to make these different kinds of detection methods work. In this case over here, you need to know what the damper position is, so you have to have access to a sensor that's telling you that, and you need access to the control system so you know what the command is. And it's actually fairly common that you don't have a feedback sensor or you don't have access to the control system. You can't make that, you can't measure that control command. In the case of the temperatures, well, this is fairly common to have both of these temperature measurements, but again, they may be in the control system. Maybe you don't have access to them. For the cooling energy, it's actually pretty uncommon that you would be metering just the cooling energy of that coil. It's not all that common for a rooftop unit or an air handler to have that measurement. So this creates a challenge. And I think anytime that you're thinking about fault detection and diagnosis, you really need to think about, well, what data are required to use my method? And I know that one of the parts of the challenge is actually to think about using different levels or tiers of data in order to do FDD. And it's preferred that you can still do FDD effectively with kind of a lower amount of data, or higher level data. Okay, so we've talked a little bit about detection for this one specific fault. And now I want to think a little bit about diagnosis. And so obviously, there may be other things that could go wrong with your air handler other than just the damper getting stuck. So if you determine that there is a problem, then you have to think about, okay, well, how do I diagnose this problem? And so what I'm going to present next is one possible approach to thinking about diagnosis. And mainly it's just to get you thinking kind of about pattern recognition and how you recognize or identify what's going on. So before we were looking at a schematic of an air handler. Now what we're looking at is actually an illustration of the different kinds of control modes that an air handler has. And I'm going to take a second to explain this. Now let's go back and review it in more detail. But the idea here is that if we know how the controls should operate, then we kind of have a pattern that we can watch for. And if we somehow see deviations from this pattern, well, we can use that to help perform fault diagnosis. Okay, so as the outside air temperature increases from very cold to very hot, you sort of move through these four general stages of operation. And this is pretty abstracted. The specific controls in certain cases will make these curves look different, etc. But you'll get the idea here. When it's really cold outside, you don't want any outside air because that outside air is really cold. You obviously don't need to cool the building. You actually need to heat it. So this bottom plot here is showing the percent heating that you're applying. Now, this could be from a hot water coil. It could be from a natural gas fired coil in your air handler. But whatever it is, at some very low temperature, you're running this flat out. And then as it gets warmer, you have to use less and less heat until at some point you don't have to heat your building anymore. At that point, typically what happens is you actually have to start cooling. But the outside air is probably still fairly cool at that point, so you can use your economizer. At that point, you start bringing in more outside air to keep the temperature of the building stable. And as it continues to heat up, eventually your economizer is open to 100% outside air, but you're still not able to cool the building adequately. So at that point, you start using your mechanical cooling system. That could be a chilled water coil, or it could be a compressor system, as is the case with most rooftop units. And as you proceed, you're still economizing, but you're also using your mechanical cooling system, your cooling coil. And then finally, at some point, it gets too hot outside. The outside air is just too warm to be economizing anymore, so you have to shut that outside air damper down, and then you continue using your mechanical cooling. So those are the four general control modes. What happens if we have a fault with our economizer? So let's look at that fault that we were talking about before. If the damper is stuck, instead of following this nice pattern as the temperature increases, that damper is just going to sit at the same position all the time. So you can see the bold line here is basically what's actually happening, and then the dashed line is what should be happening. So if that damper is stuck, you'll see that, well, we actually have to start cooling at a much lower temperature because we can't do any effective economizing. And we actually have to start heating at a higher temperature because we're bringing in more outside air than we need when we're at kind of low temperatures outside, and so we're performing additional heating. So this is a signature that if you watched the operation of the unit long enough, you could possibly look for. Even if you didn't know anything about the outside air damper, you might be able to look for this signature or pattern in the cooling and heating coils. So this is one potential way that you could look at the behavior of an air handler and determine, is this a stuck damper fault? What does the pattern of operation look like over time? Well, here's a bit more subtle fault. What if you just had a biased outside air temperature sensor? So in this case, everything's operating properly except your temperature sensor is reading too high. So for example, if it's actually 70 degrees outside, your temperature sensor might say that it's 80 degrees outside. And this is fairly common. I mean, if you've ever gotten into your car on a hot day and you happen to have a dashboard temperature sensor, you turn on your car and that temperature sensor says 130 degrees. Well, it's because it's underneath the hood in the sun and it's very warm, and then you drive for a few minutes and that temperature comes down. We have the same problem in air handlers where the temperature sensors may be in the sun, or they're kind of in a shielded location that's too hot, or maybe the sensor is just drifting. In any of those cases, it'll read too warm. If it reads too warm, it's basically going to shift all the controls for the damper down because the system thinks that the temperature outside is actually warmer than it really is. So what does that do? Well, it means that you open your economizer, your outside air damper in your economizer earlier, and possibly you need to be heating, therefore, at an earlier point in time. So your heating pattern is going to change. You're going to be heating for longer at higher temperatures because you're bringing in too much outside air. Similarly, kind of as you go up, you're going to cut off at a lower temperature than you really should, and that's going to increase your cooling when it's very warm outside. And finally, let's just look at one real extreme case here, which would be if your damper controls are just flat out reversed. And this does actually happen, although it's usually caught during the commissioning process, where somebody has wired up the control backwards so that when they think it's open, it's actually closed, and vice versa. So you see here, we just kind of flipped this whole pattern upside down. Every time that the damper is supposed to be 100% closed, it's 100% open, and vice versa. So what happens here? Well, we're going to see a large increase in the heating and cooling load because basically at the extreme conditions, we're bringing in all this outside air that has to be conditioned when you don't want to be doing that. And only at this one point is the outside air ever the correct amount. And also with this kind of situation, you're likely to see comfort problems because when you're bringing in all that outside air, you're not very likely to be able to keep up with the heating and cooling demands of the space. So that's 3 different patterns that you might be able to look for and recognize. And if you had some system that was looking for these patterns over time, then you could use those patterns to help you perform fault diagnosis. Okay, so then just some food for thought. I'm not going to try to answer these questions, but they should be things that you should think about. Well, one of those is, hey, how do I recognize these patterns if I don't have all those measurements? Can I get away with just looking at some of the measurements? Is there some other way that I could look for patterns kind of in other data? The other thing here is, what if you don't want to wait for all those different outside air conditions to look at these patterns? You have to look from when the temperature is very cold all the way to where it's very warm. Well, that might take a long time. What if you don't have that much time to perform diagnosis? And then third, what about other types of faults? What if there's something else that's wrong that you don't have a pattern for? How are you going to be able to tell how it's different from something that you've already looked at? So those are some of the challenges that are faced with when you are trying to develop a diagnosis algorithm. Now, just real quick before I talk about some of the open challenges, I want to talk about evaluating AFTD algorithms. And this is important because whenever you're trying to say whether or not a building is experiencing a fault and what that fault is, well, your algorithm could get it wrong. And so you have to think about what are the implications of getting things wrong. So in this diagram, we're taking input samples, that's basically data, and we're feeding those data through fault detection step and then later through a fault diagnosis step. And so in the fault detection step, you kind of have 2 outcomes. Either you say, all right, it's the building is not faulted, it's fault-free, or you say the building is faulted, there's a fault in my building. And then in either case, you could be right or wrong. So if there is a fault, but you said there wasn't, you're over here at false negative. But if you got it right, that really the building is fault-free, this is a true negative. This is where you want to be. You could have no output, which is not very helpful. You could have the case where you said that there was a fault, but actually nothing is wrong. This is a false positive, also known as a false alarm. One of the biggest complaints with fault detection and diagnosis as currently implemented in lots of buildings is an overabundance of false alarms. The system is telling them that things are wrong in the building, but there's nothing actually wrong. And false alarms are very costly. They get people to go and check out systems, so they involve a lot of labor and time. And therefore, if there are lots of false alarms, then building owners and operators will get annoyed and stop paying attention to a fault detection diagnosis system, and then it won't really be useful anymore. So where you want to be is over here, only telling the building owner or operator that there's a fault when it actually is. And so we call that a true positive. And so once you've got that true positive, you come down here to this diagnosis stage. And this is fairly straightforward. Either you have the correct diagnosis, or you don't have the correct diagnosis, or you don't have enough information and the algorithm doesn't give you any diagnosis at all. And so as you're thinking about developing your AFDD algorithm, you have to think about, well, how often is my algorithm likely to fall into these different buckets? And there are lots of metrics out there that you can find that will talk about the different ways that you can compare these different buckets and these different outcomes in order to draw some conclusions about how well the algorithm performs. All right, so finally, let's talk a little bit about the open challenges for fault detection and diagnosis algorithms. I've listed 8 here, but I'm going to really concentrate on these 4 that I've put in bold. And these are the ones that I think are being addressed specifically in the Jump into STEM Round 2 challenge. One that I've already talked about is this lack of sensors or data. There are lots of cases where it's difficult to get access to the data that you need to really perform adequate fault detection and diagnosis. Either the communications isn't available, or the company doesn't want you to access that data, or the sensors just don't exist. And so algorithms that are able to perform FTD using fewer data are highly valuable. The second one is one I just touched on, which is poor FTD performance or high false alarm rates. High false alarm rates both reduce confidence in FTD algorithms, and they cost a lot of money. So algorithms that can perform better and have lower false alarm rates are preferred. Of course, there's always a trade-off between lowering your false alarm rate and how sensitive your algorithm is. So you kind of have to think about that too. Third, I believe the challenge references the ability of people to understand and respond to FTD outputs. Your diagnoses have to be useful. You need to be able to communicate kind of exactly what's happening and why it's important. And this ties in with this last point, which is understanding the value of FTD. How do you communicate to somebody who's using an FTD tool how much energy or money is being wasted and how much fixing the problem would save them? And then can you communicate like how much energy or money can be saved by the use of the tool overall over a period of time? And just to kind of illustrate like a couple of places where these issues really matter, let's talk about smaller buildings. So when we talk about lack of sensors and data, most FTD algorithms that are out there use a building automation system, which is just the control system that controls the HVAC and other equipment inside of a building. And this kind of automation system typically has a lot of sensors connected, and if you can connect to that, you can get a lot of information out of it. Unfortunately, when we talk about small buildings, only 8% of them have an automation system. Most of the rest use like a residential type thermostat. So this presents a real challenge if you need those kinds of data. Also for small buildings, there's a real challenge regarding cost. With traditional rule-based systems, you have a lot of engineering labor that's required to set up and configure all of the rules. But when you look at small buildings, you can't afford to spend a lot of time on all that engineering labor, just because even if you had 20% energy savings that could be guaranteed by using a tool, if you kind of do the math on the return on investment for that, it's only worth it if you're spending between $2,000 and $4,000 on your fault detection diagnosis tool. which is actually well below what the typical cost for deploying a fault detection diagnosis tool is for a larger building. So that's just a couple of categories or a couple of illustrations to help you think through some of the challenges. And that's the end of the presentation. I did want to mention one more time that right here at the end, the references that were above are provided, so you can go back and find the papers and reports and websites that were referenced. And hopefully that will provide a starting point for thinking about different types of FDD algorithms and how you might implement them. I think we have a few more minutes. If there are any questions that came through?
Yeah, so if folks want to type any questions into the chat box, I'm going to go ahead and try and take control from you here. Let's see if I can do that effectively. And are you seeing my screen, Steve? Okay, great.
Yes.
All right, so if you have questions, go ahead and type those into the chat field. I'm going to actually do a little bit of driving over into our actual website here on jump.ideascale.com for a second to show you round 2. So I'm on the home page, and if I click round 2 here, Steve, are you still seeing my screen, hopefully?
Yep, we are.
Great. Okay, great. So this is the challenge that we've been talking around, trying to do designing new methods for fault detection and diagnosis in buildings. And I think, Steve, you did an awesome job going over the real 101 on understanding what is a fault and what are the diagnosis needs and how we might think about these problems. But I wanted to scroll down here to show you a bit about this challenge that here we're asking for the identification of what types of faults are and when they occur, a method for indicating for how you might identify the fault per the different level of available data, the energy savings potential for fixing this fault, and a method that will help owners visualize the fault. You'll be using the data that is provided. There are 3 sets of data that have been provided. The first webinar, which was just recorded and will be posted shortly, right here is where it will end up being posted, is all this data is right here. So all of this information is on this card. So do check it out. A few more things to share with you. I'm not seeing any questions type in. Our next webinar is next week. This should be another fantastic bit of information, real-world experiences from Jared Parker, who's with Michigan State University. He's using some of these tools to try and understand what's going on with his buildings, and so he'll go over what that's like, the perspectives, and some of the challenges he's facing. So register for that. That's on October 30th at 2 p.m. East Coast time. And then another plug for the upcoming round 3 challenge. This is another opportunity for students to get involved and compete for this opportunity with an internship at Oak Ridge or NREL. It will focus on the envelope, so that's the wall system. So thinking about wall retrofit designs, using a base case house to design a product that will meet local code, address material needs, efficiency levels, air tightness, and the like. We also want to see a demonstrated performance for moisture and air tightness requirements, and of course, improved energy performance for the building that it's being used in. So this challenge will be launched in a week or so, early November. So do check back and get involved if you're interested in that one. And there will be webinars associated with it. So more fantastic opportunities for you. Let's see, I do see a couple questions here. So let me, Steve, is your line open? Because I'll ask you this question.
Go for
What
it.
kinds of careers Here's the question. What kinds of careers are associated with fault detection and diagnostics? How do I get into this field? And what classes can I take to learn more about this?
Okay, so let's see. Careers associated with fault detection and diagnostics. So there's a few different places within the kind of industry ecosystem for fault detection and diagnostics that you might think about. One is on the developer end. So there are careers in software development, in algorithm development, and kind of mechanical and electrical engineering, as well as careers with machine learning algorithms and things of that nature that are all around actually developing the tools themselves, doing the research that's required to figure out how to best detect and diagnose faults, and then implementing it in software. Then there's a whole class of folks that are typically either mechanical or electrical or architectural engineers, something along those lines, or people that have picked up industry experience along the way, who are actually using those fault detection and diagnosis algorithms and selling services to building owners and operators to perform FDD. And so you might see retro commissioning companies or energy audit type companies. A lot of those smaller consulting companies are providing these services. Finally, there are careers with energy management and information system where you're actually working typically for an owner of a building or an owner of a portfolio of buildings you are actually managing those buildings for them and helping to look at the fault detection diagnosis outputs and then acting on those outputs to repair the building. And of course, there are always kind of other careers associated with these companies, such as marketing, sales, financial analysis, and etc. And often with fault detection diagnosis, these are especially important because you really have to understand kind of how to quantify the value of these tools and how to be able to communicate that clearly. Let's see. There was questions on classes. Is that correct?
Yeah. So what kind of classes will help you learn about all this and get involved?
Yeah. So if you have a building science program at your college or university, that's a really good way to learn about building systems. However, you can also look into other classes on kind of the algorithms themselves. So if there are classes on machine learning algorithms, that'll help you understand how those work, and especially on kind of clustering and classification problems that are sort of these abstract mathematical problems, but they have a lot to do with how fault detection and diagnosis algorithms work. So I would recommend that. And then there's a lot of reading that you can do that's not, technically coursework, but there's a lot of good industry material that's available via the web or DOE's websites or other locations where you can just kind of get some background.
Great. Here's another question for you. Maybe you can speak to this. What kind of visualization are you looking for in our challenge idea? What kinds of things should we consider when trying to, present visualization of the information?
Yeah, that's a good question. And rather than, I think, give an answer in terms of like what the visualization should look like, I think I'll answer it in terms of what information you're trying to convey. Typically, you're trying to convey to whoever's using a fault detection diagnosis tool. You're trying to communicate clearly that there is a fault, where that fault is, what that fault is. That's kind of the basics. But then if there are multiple faults, you want to clearly convey which ones are most important. And if you have a system that's generating lots of different alarms, you want to kind of clearly communicate what is the source cause, what's the most important of those alarms to look at. And then the third thing is that it's often hard for building owners and operators to justify fixing faults because they don't really know how much impact they're having. So ways to clearly communicate what the either the energy impact is or even better is the dollar impact of fixing versus not fixing that fault, so that decision makers can kind of quickly come to a decision on, well, should I postpone this until the next regular maintenance, or do I need to fix it right away? Those are the kind of three things that I think existing tools don't necessarily do very well, that can really help a decision maker.
Great. So there's another question here on what's the difference in faults for commercial buildings versus residential buildings?
Yeah, so there's differences in types of faults as well as differences in the kinds of approaches that are probably going to work well. So residential buildings, you have much simpler systems. You typically have your house is one or maybe two zones. So a zone is an area of control. You're controlling the temperature for the whole house together, or maybe by floor. Whereas in a larger commercial building, you have lots and lots of different zones, so your control systems are much more complex. So within a house, you're typically looking at kind of physical problems in the heating and cooling equipment, so your air conditioner, your furnace, stuff like that. You may be looking at actual leakage in the building itself, or poorly sealed ductwork, things like that. And in a larger commercial building, there's a lot more opportunity to have what are called control faults, which are just errors in the way the control programming is done, such that you're not optimally controlling the various systems. They're fighting each other, or you're wasting extra energy, or things like that. They don't have a whole lot to do with the actual physical equipment itself, but have a lot to do with the controls of it. Other than that, commercial buildings basically have the same kinds of systems that are in a residential building. They're just more complicated and bigger. So a lot of the faults are similar. You can have air leakage faults in both kinds of buildings. You can have problems with your compressor system in an air conditioner in both kinds of buildings. But when you're thinking about commercial buildings, generally it's a larger scale, more complex version of the same problem.
Right, right.
I should also mention that.
Go ahead.
Yeah, I should also mention that in residential buildings, it's actually a whole lot harder to come by data because it's harder to put in sensors. It's harder to justify the cost of those sensors, and generally the systems don't communicate the same way. So actually the data problem is much worse in smaller buildings, and particularly in residential buildings.
Okay, awesome. Well, not awesome, but awesome challenge for our students to think about, right? We want you, and we want your ideas. Stephen, thank you so much for a great presentation here and discussion of fault diagnostics and detection in buildings. I don't see any other questions, and we're pretty much at time. So I hope everyone has a great afternoon, and look for a recording of our webinar. Thanks, Stephen.
Okay, thank you.